No, I haven't heard back from the testing center. I don't even know what your grades are yet either. So, but it looked like about 2/3 of you decided to take the retake. So, and the large majority did phenomenally well. It's nice when it's open book, right? So good. So if you didn't do well Wednesday, that'll definitely help you. Well, new unit. So with that, now that the retake is closed for the exam one, you can go and see all the answers and my explanations, the solutions. And I'm happy to discuss those, but you might as well look at them first because that's why I wrote it. But if it still doesn't make sense, we'll talk about it Monday. Because the final is comprehensive, and so I will ask questions from that material on the final, and if you don't understand it, it would behoove us to do so.
You write the final, right?
I write it all. And final will be the same type of format, just longer. Yeah. The final, you won't have the opportunity to do a retake. All right, so we finished chapters 1 through 5. That was science, motion, Newton's laws, forces, acceleration, velocity, speed. You know all this. You just took the test. Now we're going to extend it to chapter 6 and 7, chapter 10, and then chapter 35. This is all on WebAssign, the calendar, and as your assignments pop up. In other words, we won't cover 8 and 9. We'll come back to some of these, but this is our next unit before the next exam. It's those chapters. 6 is momentum. That's where we start today. 7 is energy. 10 is 2 dimensions. Projectile motion. In this one, we won't cover all of chapter 10. So everybody listening, the stuff on orbits, I will not be testing you on. I might mention and relate some stuff, but the stuff on the orbits, I won't be testing you on. It's an easy extension from this, but. And 35 is Einstein's special theory of relativity. And those of you freaking out, no, well, you know everything you need to know to understand it right now, actually, after this unit. I give you the rest. We're not going to derive the stuff, you know. But it's fun. People have heard of it. They know about it. And we have enough, you're armed with enough knowledge now to wrap your head around it. And it's kind of fun, some of these thought problems and the consequences from this theory. We use it all the time in the world around us. We rely on it, actually. Scientists and engineers have to take it into account, or our world wouldn't work the way it does with our technology. And we'll explain that more when we get there. So I'm going to expose you to some of it. It'll be fun. And then we'll have exam 2. So today, we'll start with momentum. A couple days of that, couple days of that, couple days of that. You get the idea. There's an overarching concept with the first half of this unit, with momentum and energy. It's conservation. Both of those are conserved. And they'll both discuss that. The one you're probably familiar with, energy is conserved. You can't create energy, nor can you destroy it. It changes forms. It might be all the energy's over here, but then it transfers into this. Or maybe the thing's moving now, but now it's not. Work can be done on things to change the energy. It just moves around. You can't magically create more of it, though. Well, there's the same idea with momentum. And we'll discuss what each of these are as we go through them. And then the second half is back to that motion stuff and forces. Armed with this, it'll make more sense. But this is just more motion, just expanding it in 2 dimensions and with the special theory of relativity, going faster and faster and faster. Things change with fast motion. All right, so you guys have all heard the term momentum. How would you define it? You know, your friend on the street, your mother asks you, what's momentum? What would you tell her right now? What do you think the dictionary says it is? Not me, your physicist instructor. What do you think the dictionary says? Somebody give me one little bit and we'll add on to it. We'll try to piece together what momentum is. Yep.
A moving force.
A moving force. Okay, good. Add to that. Velocity times mass. The actual equation, that is what momentum is. Mass times velocity. Okay. Does that mean anything to you yet? Okay. So something to do with forces, something to do with mass and velocity. Direction. Yeah, I'll give you momentum is a vector. Since velocity is involved, it's a vector. Momentum is also a vector. So direction is involved. Good. See? Put the pieces together. This is our reasoning part, right?
Like how much energy it carries with it?
Good. I'm glad you said, yeah, how much energy it carries with it. I'm going to put energy in quotes. We're going to learn technically momentum and energy. They're different things. Historically, my term is like oomph. If something runs into you, it like transfers something to you, right? It's like oomph. They didn't know what that oomph was. They hadn't termed momentum and energy yet, defined them specifically. They just, again, my term, something called oomph. You know, if you dropped a ball in like Play-Doh or clay, you ever done that in something squishy, sand even? It makes a dent. Well, how big a dent will it make? It depends on its momentum. It depends on how much energy it comes in with. Do you think it'll make a bigger dent if I drop it from a higher height? Yes. Well, how is it related to how fast it's going? What if I threw it at it? You know, its incoming velocity. Would that affect the divot? Yeah. So they started quantifying this. They did an experiment. They would drop it from different heights. You guys now know how the height relates to the speed. So did they. How does the speed carry? You know, if I drop a ball from this high, how fast is it going when it hit right before it hits the ground? You guys are all going. Is your first thought, oh, I don't know how to do that. You do. We didn't do it, but you do. Acceleration was a change in velocity with time, right? So, change in velocity is acceleration times time, yes? Your change in velocity is your final minus your initial. Whoops. And that we wrote as the final is however fast you were starting plus the change. Add it on to the 0 or whatever fast you're going. You know the acceleration due to gravity. You can time how long it falls. If you let go of it, what's the initial velocity? 0. Yeah, so, you know, let's make this up. If it falls for 1 second, you know how fast it's going after 1 second, I hope by now. 10 meters per second. Well, let's see. If it started at 0 and it went 10 meters per second every second for 1 second, yeah, you end up at 10 meters per second. So you know how fast it's going based on how long it fell. You drop it from higher up, it goes faster. So they knew that. it was great. They'd have historically debates over this. Oh, I think it's momentum. I think it's energy. What is this oomph? So not until they actually did some measurements. Like us, seriously, as simple as taking the cart and with the time interval, 1001, 1002, 1003, and mark where it's at. They would drop a ball into some clay and measure how deep it went. They figured how deep it went was proportional to this oomph. And they realized, long story short, the oomph was energy. And it was great because it was a female that did it back several centuries ago when female scientists weren't as well respected. And she's the one that did the experiment and got it right. And then everybody listened to her, and we are where we are today. But it was funny. They would just talk about it, and she went and did it. So, Châtelet, Émilie du Châtelet. She's French. She was a good friend of Newton, I think. You can go Wikipedia her. So it was related, but then they could start differentiating. So back to, okay, great. That was a nice story, Adam. What's momentum? It's everything you said. I would sum it up as inertia in motion. Instead of a force in motion, I would say it's inertia in motion. Inertia is a property of matter, and it's based on its mass. You guys know this. If I threw this 10-pound medicine ball at you, would it be harder to stop it? What if I threw the tennis ball at you with the same velocity? Which one's easier to stop? You know this has some oomph. Yes, it would have more energy associated with it. It also has more momentum. Its mass, more inertia, more resistance to changing its motion. You're the one exerting a force trying to change its motion to stop it, to go from some velocity to zero. There's your change in velocity. That would require more momentum change than it would for this. This one has more momentum because it has more mass.
So for example, in the one example where you had like a bug hitting a windshield, the car has more momentum than the bug.
That's a good question. So the bug hitting the windshield, who has more momentum? Let me say my next spot, and we can totally qualify it yet, because there's still a depends on that. Based off of mass alone, so it leads right to it. If they were going the same speed, the car has way more momentum. And that is the definition, or the equation, as somebody already mentioned. Good job. Momentum is defined with the lowercase p. I don't know why. Mass times velocity. That's momentum. Here's this property of matter we use to measure it with mass. That's the inertia part, right? It's inertia, but in motion. So we're all over Newton's first law. We know something with more mass, it's harder to get going. It's harder to stop. But when it's in motion, we can define it as inertia, momentum. So could the tennis ball ever have more momentum than the medicine ball?
It's going faster.
Yeah, absolutely. I like to ask, who would you rather get ran over by? A big Mack truck, big diesel, a Mack truck, going, 10 miles an hour? Or little Timmy on a tricycle pedaling at the speed of light? I hope you'd rather get run over by the truck. See, your intuition's right. The little Timmy would have more momentum.
Die faster.
Even though the truck has more inertia, more mass, the product of mass and velocity is less for the truck than it would be for little Timmy. Not much mass, not much inertia, but going really fast. So both come into play now with momentum. So back to the bug and the car. I don't know who was going faster. But in theory, the bug's just kind of do at slow speeds, and the car is coming down the highway. So I'll still go with the car in most practical cases. And there's our guide to the thinking. We just discussed it. It's how they came up with it. Momentum, they knew it was proportional, directly proportional to mass, and it's directly proportional to velocity. And this one worked out to be exactly equal. No constant of proportionality we have to throw in there. That's what it is. So we say things have momentum. But there are two things, review, that we said we don't like to say. What do I want to? Okay, it's not coming out in my head well, so just say it. I asked you this before. Can an object possess force? Very good. Yeah, we don't say it possesses force. Why? Do you remember? Because the force acts on it? Somebody over here? Yeah, they all come in pairs. So you don't have one isolated. So you can't just say, yes, I possess force. It kind of sounds funny anyway, right? I can possess energy, the potential to exert a force and interact with something. But we don't like to say objects possess or have force. But we do say objects can possess momentum. They have momentum. I've just been doing that in this class. Because it possesses mass and velocity. Yeah, that's why. So, second term. Acceleration was force over mass, Newton's second law. And, we already did it, acceleration is a change in velocity with time. So, nothing new here. I'm just going to write them like this. They're equal. Both of those are acceleration. So this is equal to that. If we rearrange it, I'm going to multiply t by both sides and m on both sides. Or for those of you that remember your algebra cross multiply, you end up with the force for a given amount of time equals the mass times the change in velocity. This is the change in momentum. If you're going one speed and then you go change to a different speed, you've changed your momentum. You went from mv something to mv something else. And that is called impulse. It's with the letter I. Impulse is defined, three of them mean defined as impulse. So, technically, the change in momentum, you have a change in mv, and that's a force for a given amount of time. Throw in the delta sign to emphasize it's for a certain amount of time. So there's your two new equations. You know what momentum is. An impulse is a change in momentum. We usually refer to it as impulse when we're talking about the force in time. And we refer to it as change in momentum when we're talking about how the mass and velocity change. They're the same thing, though. I want to emphasize, change in momentum is the exact same thing as impulse. Two terms for the same thing. If you want to change somebody's momentum, what do you have to do to it? Exert a force on it. Which means there's a net acceleration, which means its velocity changes, and if its velocity is changing, so is its momentum. Well, can you apply that force instantaneously? No, it always takes a finite amount of time to apply that force. So, you apply a force for a given amount of time, that causes a change in momentum. And in most terms, that relates to a change in the velocity. Can you think of an example where something's mass is changing? Bet you can. Yeah. If two objects combine, yeah, say it's just accumulating, adding more and more mass. Yeah, that would work. Can you think of a practical example of something that might do that? You add to it and it just increases its mass? Or what were you going to say? When you go into a black hole, your mass does change. It actually increases. Yep. Yep. Ice melting, very good. You got mass of an ice cube, but as it melts and turns into water and evaporates away, it leaves. And so, yeah, its mass decreases. So its momentum would be changing if you threw the ice cube, and it melted along the way. Yeah. Yep. Car burning up the fuel, or more conspicuously, a rocket. If you keep throwing the fuel out or using it up, your mass decreases while you're moving. Great example. See, I knew you could do it. Another classic example is a coal train. The train comes by with the coal carts, and they put the coal in, and it makes it heavier. So that changes its momentum. So momentum can change. You can have an impulse if your mass changes and or your velocity changes. But for most of the things we notice, it's just the velocity. All right, let's do this one. Anybody a pitcher in here? Like to throw things? Now's your chance. I'll use a volunteer, otherwise I'll throw it. But who wants to throw this? It's a squishy ball. Okay. All right. To emphasize some of this, we'll do some demos. Here's a squishy ball. It's a little harder to throw than a baseball because of the way you hold it, but I'd like you to throw it and hit that mess up there. Beautiful. Stay here. I like as it emphasizes interactions, force pair interactions, this on the board back on this, often happen quickly. And so we don't take note of this time, this delta t. Look how much this expands while it was in contact with the board. That's while force of the board back on the ball caused it to slow down and decelerate, right? Stop, and then accelerate it back up and bounce off. It had to go. What do you think he has to do to increase that diameter? Throw it harder. We can still see it. Let's see here. Sure. Let me move. You're consistent. Hey, all right. Can you see that one's a little bigger? Wonderful. Thank you very much. See, isn't that fun? So yeah, if you adjust the forces, you can adjust the times of the impact. I could get this 10-pound medicine ball. I'm going to change its momentum. It has none right now, correct? Because it's not moving. And I get it moving. Now it has momentum. I applied force. What if I do that faster? If it still gets up to the same speed, how did its change in momentum compare? It started with what momentum? 0. And it got up to mv, whatever that velocity is. Well, there's different ways to get it up to mv. You can push it quickly or slowly. But it still has the same change in momentum. And if the change in momentum is the same, what else do we say is the same? Impulse. Impulse. In order to make that happen, the force would have to be different. Let's Draw that relationship. If you have a case where the change in momentum, thus the impulse, is the same, we have the same change in velocity and we're not changing the mass, then the momentum changes the same amount. You can apply a big force or a little force. Tell me what else will adjust then to balance that equation. The time. Who will need to take longer? So you can apply a big force for a brief amount of time and have the same change as if you did less force. It'll just take longer. You'd have to push it for longer to have the same effect. That's the fun part with change in momentum and impulse. All right, now I need 3 volunteers. We're going to throw eggs. No pitchers in here? If you'd like to help, come on down. I need 3 volunteers. I can't. 1, 2. John, will you help us out? No pressure. You can't mess up. Seriously. Well, if you hit them in the face, maybe they might not like you, but I've never had that happen yet. All right, I'm going to have you two hold the sheet. And I'm going to have him throw an egg into the sheet. All right, so hold that corner with your left hand. You hold that corner with your right hand. Hold the opposite corner with your other hands. It happens. I'm prepared to deal with it. All right, you're going to hold. Here, you move that way a little bit. You scooch as far as you can. We're going to aim this way. Hold that up as high as you can. Back this way a little bit. There we go. And this, yeah, keep it curved like that. That way, if it doesn't break when it hits this, you can catch it.
Gotcha.
All right. Your job is take a fresh egg, and this is harder than the baseball too.
Yeah.
Is you're going to hit the sheet. And your job is to try to break the egg when it hits the sheet.
Okay, so I can even throw it from like here.
You can get as close or as far away as you want. I've had the egg go about everywhere, so you might start slow. You can have another throw. Just don't hit them. And is anybody sitting behind? You just heads up. All right. Whenever you're comfortable. Boom. It didn't break when it hit the when it hit the sheet. It did break when it hit the ground. I got another one. That was good. It did. Witnesses, did it break when it hit the sheet? They're ready for you now. Faster. Ooh, that is the best. That's the best I've had anybody go after. Thank you. Thanks all 3 of you. I appreciate it. I'll go get a paper towel. So the points here, it worked great twice. The egg didn't break either time, even though it came in with a lot of momentum because it was going fast. And what did its momentum end up as? 0. So there was a change in momentum. What created that change in momentum? The sheet, exerting a force back on the egg to slow it down and stop it. So the sheet applied a force for a certain amount of time onto the egg. But it wasn't enough force to break the egg. Why? It slowed it down. It extended the time that the force was applied. The sheet gives a little bit. Does the floor give? No. That one broke even more than the first. Why does it break when it hits the floor? Yeah, the floor doesn't give. Who felt more force, the floor or the egg? Oh, bless you. They're equal. But the egg couldn't take that force. That was too much force. How did the force the egg felt from the floor compare to the force it felt from the sheet? The force the floor on the sheet to stop it, floor on the egg, compared to the force of the sheet on the egg. They both stopped it, didn't it? So they had the exact same change in momentum, the exact same impulse. But the time was different. So this was the sheet, less force, not enough to break the egg because it extended the time of the collision by giving. This was the floor. It was a brief amount of time of contact, so it needed a lot of force to stop it, to have the same change in momentum, thus the same impulse. Does that make sense? All right, let me get this before it starts smelling. Yummy. Questions or concerns? Well, it looked like both of those eggs felt the exact same impulse. They had the exact same change in momentum. They went from mv, however fast you threw it, to 0. Okay, sure, I was dropping it, but say you threw it right against the wall. They would come in with the same momentum, and the momentum would change to 0 the same amount. So these were identical in both cases. But in one case, it broke. In the other case, it did not. What makes it break? The force. The force. The egg couldn't take that much force when it stopped quickly. So same things. How many of you have ever done the toss, an egg toss or balloon toss? Water balloon? How do you catch one of those? Yeah, you cradle it and you kind of give, right? Don't you? Why? To extend the time of impact so it doesn't break in your hand. So that your hand doesn't have to apply as much force to the water balloon or the egg to create the same change in momentum. That's what a helmet does. We say, oh, it's because it's padding. What is the padding doing? It extends the amount of time. You can also look at it as it extends the distance it takes to stop also. That takes time. Either way, it extends the impact, the distance or the time. When you talk about the distance, you talk more about work. I'll review that when we get to energy. But for change in momentum, it deals with the time. Did we have any high jumpers or pole vaulters here? You land on the pad. You go up really high on the pole vault. My brother did that. What do you land on? Nice cushiony pad. And so you don't break your legs when you land on the ground, right? And that, again, it extends the time of the collision. So I can't emphasize enough here at the beginning. The impulse would have been the same, whether you used a pad or a helmet or not. You go in with some momentum mv, and you get stopped. Do you want to do that quickly or slowly? Slowly if you want to survive. Here's another, I like this demo a lot to drive this home some more. I have two spheres here. The bouncy ball and the not bouncy ball. People often refer to these as the happy ball. and the sad ball. Well, I'm going to roll them down the ramp like this. And see if they can knock this block over. All right. Do you think either of them will knock it down? Who thinks the sad one will knock it down? Raise your hand. The one that doesn't bounce. Raise your hand. I'm interested. All right, who thinks the happy one? Any takers for that? A few, but less. Anybody think both will? A few takers. Neither will. And everybody thinks it'll do something. All right. Well, let's start with the sad ball then, since you guys thought it wouldn't. I mean would. Ready? Could have been a fluke. Repeat the measurement. Come on. Am I high enough? Okay, it doesn't knock it over. That's the sad ball. Let's try the happy ball. Boink. Piece of cake. Boink. Any ideas why the happy ball, bouncy ball, can knock it over while the sad, no bouncy ball can't?
Perhaps the velocity is greater?
Okay, let's look at velocity, and that could be different. If they start at the same height, these have the same size, they're both made out of rubber, they weigh about almost identical, how do you think their speeds will compare right before it hits the block? Yeah, they're identical speeds. So they come in with the same velocity right before it hits the block, which also means they have exactly the same amount of momentum going into the block. MV. MV. Other ideas? Yes? Yes, these both give. They can both squish. That might explain why one bounces and why the other one doesn't. So that's true, but how does that relate to knocking the block over or not? Landing versus jumping. He's getting to it. Do the two balls do the same thing? Now let's watch this ball. Boing. Boing. Yeah, this one's rebounding. It's like jumping back up, where this one just stops. So let's look at the change in momentum for both of these. Let's start with the sad ball, no bounce. It comes in with MV, initial momentum, initial velocity. It's coming in with that. What's it go to when it hits the block? What's its momentum change to? 0, right. So its final momentum is 0. MV final is 0, because V final is 0. It stops. So its change in momentum is the final momentum minus the initial momentum, which is MV final minus MV initial. The final was 0. So its change in momentum was a negative MV. Do you see that? Let me pause for soaking in. I know I just wrote a bunch of stuff down. So it came in with MV in the positive direction to our right. The change was a negative MV to stop it. It got pushed this way. All right, let's do the bouncy ball. What's its initial momentum? 0? What's its initial momentum right before it hits the block? How do we find momentum? Mass times velocity. It's essentially the same mass. It's a very, 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 very small difference. And what's its velocity compared to that one? Yeah, it's the same. So it comes in with the same initial momentum. What's it go to? What's its final momentum? It rebounds and bounces back this way. So it has some momentum in this direction. It's some, here, we'll idealize it for now. Let's say it rebounds with the exact same velocity it came in at. You know, it comes in with V, goes back up with V. In real life, it comes back a little slower. Let's just make our math easy for now. It's something. So the final is the same as the initial, but in the opposite direction. If it's coming in with positive momentum and it rebounds back that way to your left, we just throw in a negative sign, right? Because the force applied to it, the block, pushed it that way. It was coming in, it stopped it, and it pushed it back. So it was always pushing that way. So what's its change? Its final minus its initial. This is the final. That's the initial. And what is that? 2 mv. Negative 2 mv. Point here is the sad ball, the block had to exert enough force on it to stop it. That's all it had to do. The happy ball, it had to stop it, and then it kicked it back. So it applied force to stop it and more force to kick it back. It had gave it twice the change in momentum. That agrees. Does that make sense? So if the block gave the bouncy ball twice as much change in momentum, it also gave it twice as much force. And if the block pushed on the bouncy ball with twice as much force, what did the bouncy ball do to the block? Push the block with twice as much force. That's why the bouncy one knocks it over. The block felt twice as much force, so did the ball. Slightly less than twice because it doesn't rebound with exactly the same speed, but you get the point. Boink. So, lesson learned here. You know, when your mortal enemy's pushing you out the 10-story building or out of the airplane without a parachute, what do you want to do? How do you want to land when you hit the ground? You want to bounce? No. Who's going to feel more force? The bouncy ball. So go splat. You want to go splat. Maybe you still break every bone in your body, but you might still live if you don't bounce. What do we tend to do when we get into accidents? Tense up. What's that do? It makes us bounce. You know, actually relax. Kind of go limp. You want to go splat. You don't want to bounce. So see, in my mind, this is the happy ball. This is the sad ball. Because it feels more force. Now, realistic application. It's sad, but it's real. Who usually gets injured more in a drunk driving accident? The other person, not the drunk person. That's very typical. Why? Do you ever think about it? They're usually more relaxed because of the influence of the alcohol. So they're more like the sad ball. So when the car changes their momentum, it's less force on them. Where we are like, ah! And it's more force. And unfortunately, we get injured more. But it's the same principle. Since I set this one up, let's end with this one, and we'll call it a weekend. I can do it. We'll make it. I grew up in Kansas with tornadoes. And the wind would fling all kinds of objects and stick them in other kinds of objects. So that's what we're going to do. I got a piece of wood here. And I have a sharpened pencil and an unsharpened pencil. And I'm going to fire them into that piece of wood with this fire extinguisher. What do you think will happen? The pointy one will stick? What will this one do then? Bounce off? All right, well, let's start with the fun one then. Let's go with the pointy one. The fire extinguisher is going to provide the force for a certain amount of time while it's in the tube to accelerate it, change its momentum. The masses of the pencils are about the same. I only sharpened a little bit off. So they're going to come in with about the same momentum, just like this case. They're both going to get stopped. They're going to have the same change in momentum, the same impulse. But let's investigate the forces on it and the wood. You ready? 1, 2, 3. That one went that far through. Let's try the unsharpened, shall we? So yeah, I've seen pieces of wood, 2x4s, carpenter levels, tennis shoes stuck in the sides of houses, trees, truck gas tanks. Let's not hit the knot hole here. There we go. So this is totally plausible. 1, 2, 3. Sweet. That one went all the way through. So why does the unsharpened one have a greater effect? That tells me there must have been more force to punch right through. The sharpened pencil acts like an airbag, a crumple zone, your helmet. It gives, it squishes, it's the sheet, and extends the time of the collision. And if you extend the time of the collision, then there's less force between the pencil and the wood. It didn't go as far. The unsharpened hit it all at once. Wham! Lots of force, just punched a hole right through it. Have a great weekend.